We are at chapter 5, everyone. That's great, right? We have 2 more chapters, this one and chapter 6. This chapter is going to be over the second law of thermodynamics. And after having the long problems from chapter 4, you will enjoy these problems because they are much shorter. So that's a good thing, right? Now, we're going to start out by talking a bunch about the second law of thermodynamics. So we've got a lot of written notes first to go through, so bear with me. I know that's not everybody's favorite. I personally like doing the examples the most myself. So we got to work through all this and then we'll get to some examples. Let's start out with a scenario here. And this scenario, this is the one that is usually used to demonstrate the second law of thermodynamics. Let's say we've got this air and it's going to be contained in this container. And the pressure inside of this, so PI stands for pressure inside, is going to be greater than the atmospheric pressure. So surrounding the air, we have the atmospheric pressure. So let's write down what we just said here. So air is contained at a higher pressure than the surroundings. Now at this point in time, this is a closed container, so the air can't escape, nothing like that. So it's just in this tank, it's closed up, we got the air in there at a certain pressure that's higher than atmospheric pressure. Now let's say somebody goes along and they put a hole in the top of this container. Now we still got air here. Let's just say this is the opening. All right, so now we've got this opening. Now what's going to happen is our pressure is going to change, right? Because some of the air is going to leave the canister or the container. So now we have a pressure P. So P is our current pressure. This pressure is still going to be greater than the atmospheric pressure. This is ATM right there. And it's also going to be less than that initial PI we had over here. So it's in between these two. Now let's write down our scenario here. So if the tank is opened with that little opening here at the top, the air at the higher pressure, which is inside the tank, that air then flows to the lower pressure surroundings. Because you're always going to flow from high to low pressure. It's the same thing that happens with the weather outside. That's how you get wind, right? Because the fluid particles are flowing from the high pressures to the low pressures. Same thing happens here. We got a lot of pressure in this tank. That high pressure is going to force that air out into that lower pressure surrounding environment. Now, let's draw another tank here, like that. We got air in here. Now, eventually what's going to happen is the pressure inside of this tank is eventually going to equal out with the atmospheric pressure. So P at this point equals the atmospheric pressure. Now once these pressures are equal, what happens to the flow of air? The flow of air is going to stop, right? Because there's no difference in the pressure. It's the difference in the pressure that was causing the air to leave the tank. So now let's write eventually pressures are equal and the flow of air stops. All right, so now we have that scenario. Now this is the conservation of energy working here, right? That's what we saw there. Now, if you think about it, the conservation of energy is also going to be satisfied if air from the surroundings flows into the tank and returns the pressure in the tank to the original PI. Now, if we think about that, is that really going to happen? What do you think? Can air just kind of force itself back into this tank and repressurize to the original PI value? No, that ain't going to happen. All right, so that is not physically possible. We would have to have some sort of mechanism to make that happen. All right, you'd have to have something to force the air back in, repressurize that canister. Now, that means that just because something satisfies our conservation of mass energy equations, that doesn't mean it's actually going to be possible. All right, because both of those scenarios, this one and the one where air came back into the tank, repressurized, both of those satisfy our equations, but they're not both possible. The second law of thermodynamics is going to be used to distinguish between processes that are actually feasible and those that are not feasible and can't happen in reality. That's what we'll use the second law of thermo for. And the second law and its deductions that come from it are also used for predicting the direction of a process. We can establish conditions for equilibrium. We can determine theoretical performance of cycles. We'll talk about this in a little bit. We can also evaluate qualitatively our factors that result in the best performance. And we can define a temperature scale that's independent of the properties of any thermometric substance. And finally, we can use the second law to find ways to evaluate specific internal energy and specific enthalpy. So lots of uses for this second law. And we're going to have 3 alternative statements for the second law of thermo. I'm not sure why we have an S here. That needs to go away. First one is going to be the Clausius Statement. The next one will be Kelvin Planck. And then the third one is the entropy statement. We're going to cover that in Chapter 6. That's our chapter on entropy. So we will focus on these first 2 in Chapter 5. Let's go into the Clausius Statement. The Clausius Statement basically says that it's going to be impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler body to a hotter body. That's what the Clausius Statement says. Now, we kind of already know that. We talked about it before. Essentially, that's telling you that cooler bodies can't warm up hotter bodies unless you have some sort of external mechanism to make that happen. Okay, so that's all the Clausius Statement is telling us. Now this Kelvin-Planck statement, let's go over that. For this one, we need a term or two. So let's look at this first term. We're going to be talking about a system that always stays at a constant temperature, even though heat is added and removed by heat transfer. All right, so the thing that a lot of people use for an example would be the atmosphere or an ocean. Some system that is large is always going to have a constant temperature, even though you could add or remove heat by heat transfer. And this is going to be called a thermal reservoir. So the important thing to note here is that if we have a thermal reservoir, if that's what we say we have, we're going to have a constant temperature. Okay. Now using this term here, we get our statement. We'll say it's impossible for any system to operate in a thermodynamic cycle. And remember, a thermodynamic cycle is one where you start and end with the same properties. So we can't operate, or it's impossible for any system to operate in the thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. Right? So that is what the Kelvin-Planck statement says. Now, if you read it and think about what it's saying your system is not going to be able to deliver energy by work to the surroundings while only getting energy by heat transfer from this one single reservoir. You're going to need something else to help you out there. Now, our statement, what it says, is that we can't transfer work to the surroundings. That means work can't be positive. All right, remember, if we had that positive work, that means we had power to send out. We could turn a shaft or something, for example. So with this statement, that means we can't have a positive work. Now, it does not say that there can't be transfer to the system or that work can't be zero. So we could have an external power supply, for example, and we could still use this statement, and this statement still holds true. And we could also say work can be zero. Now, so keep that in mind. We're going to have an equation for this one, and our equation, which is simple, is just going to be that work for the cycle is less than or equal to 0. And this is with a single reservoir. All right. And notice again, we have a thermodynamic cycle. So this statement is only for thermodynamic cycles. Now let's go over irreversible and reversible processes. With this, we're going to be able to determine the best theoretical performance. And the way we do that is we're going to use an idealized process. So idealized processes, those would be like the ultimate ideal process that you could get, right? Most efficient thing you could have. Now we're going to have to distinguish between an actual ideal process and a true life, real, actual process that has irreversibilities. Now you might be wondering, well, what in the world is an irreversibility? Well, let's go over that. If we have an irreversible process, what that means is the system and all parts of its surroundings can't be restored to their respective initial states after the process has occurred. All right, so you can't do the process and then return back to what you had. It's not going to be possible. All right. Now, all actual processes are going to be irreversible. That's just how things are. Nothing is perfect where you can do a process and then go back to the start. You can't do that. Now, if we say we have a reversible process, that means that it's going to have no irreversibilities and the system and the surroundings can return to their initial states. So this is kind of like an idealized process here. We're just assuming we have no irreversibilities because every process has irreversibilities on some level. Some examples of irreversibilities, in case you're wondering what in the world all that means. Unrestricted expansion of a gas to a lower pressure, that's an irreversibility because you're not going to ever be able to get that gas back to the higher pressure. Spontaneous chemical reactions are an example. It's not like you're going to be able to undo that reaction. Friction. Friction is always one of the main irreversibilities I talk about because people see friction happening every day. All right, and this applies to sliding and fluid friction. Inelastic deformation is another one, and then there are internal irreversibilities that occur in your system, and if we say external irreversibilities, those are going to occur in the surroundings. Now, if we go back to that equation we wrote down about work of the cycle, we said it was less than or equal to 0. Now, we're going to expand on that. If it's less than 0, we're going to say that there are internal irreversibilities. So we have that. If it's equal to 0, we'll put that there are no internal irreversibilities. Okay. I always think I have this word spelled wrong because it's so long, but looks okay. So this is how we'll know if we have irreversibilities or not. Less than 0, we got them. If it's 0, we don't have them. Okay? And you'll see when we get to the examples how we'll use this. All right, so let's stop this video here before it gets too long, and we'll pick up the power cycle part in the next one. All right, I'll see you all in the next video.